Hi, I'm Ilan Raja, CEO of Scan Computers. What an absolute honour it is to be recording this message for FDL. As a bit of a background, Scan is a loyal NVIDIA partner, and we've seen over the years the huge technological advancements NVIDIA has made in parallelization. Of recent, the mass steps forward that we've seen in data. And in many ways, in doing so many of our talks, I often liken data to nuclear energy. And there's a universe of data that's being collated and created, and it's growing at an infinite rate. And combine onto that computational capabilities, especially with all the efforts that NVIDIA have put in over the years, and how efficient that computational capability has now become and being able to be distributed. It was an absolute pleasure to hear about the project from FDL. So creating a digital twin, the Copernicus Earth observation, and being able to forecast chaos using compute and billions of data points really tests where computation can go. And what an amazing use case for what you guys are doing within the formation, predicting extreme weather patterns, disaster planning, its ultimate predictability of chaos, which is such an amazing project. And we're absolutely stoked to be part of your initiative, and we'd love to donate and work with you in all the ways possible to help this kind of digital twin model come into some reality. The work done by NVIDIA, especially with the progression of GPU technology, especially with the new DGX A100 and Ampere processing that's coming out there, with a whole ecosystem of ingest with fast networks and storage, is so groundbreaking that it's well warranted to actually work with FDL to combine both these technologies. We look forward to working with you, and look forward to seeing some amazing results. Thank you.
Well, good evening to everyone in Europe, and I guess good morning to anyone watching from the US. This is Team Digital Twin Earth. My name is Christian, and I'm super excited to kick off the final presentation. Now, let me first introduce my fellow researchers, Catherine, Daniele, and Valentina, and next our machine learning experts, Piotr and Freddy. And last but not least, our team leads, Duncan, who you've seen before, and Matt. And I think I'm speaking for all of us when I say it has been an absolute pleasure to work with all of you. Now, what is a digital twin, and why do we need one for Earth? Well, a digital twin is really just an interactive model that allows us to study counterfactual pasts, presents, and futures of our planet in silico. And as you're all aware, our Earth system is extremely complicated, and so trying to simulate it in full is somewhat of a moonshot. So for this project, we decided to focus on just one subtask: forecasting the global weather 5 days in advance. So why did we decide to focus on this particular challenge? Well, meet Rosie. Imagine she's a farmer in Uganda somewhere, and Rosie wants to wait for as long as possible before harvesting her crops in order to maximize the quality of her produce. Assume there's a hailstorm coming in, and Rosie only gets to know about it a day in advance. So in that case, probably up to a quarter of her harvest is going to be lost. But if she had 5 days notice, she could probably save most of it by going out and harvest. So we've seen that in developing countries, having access to accurate multi-day forecasts is a matter of livelihood. So how are we at the moment forecasting weather? Well, in terms of multiple days, the best method we know of is numerical forecasting. Now, unfortunately, we cannot just increase the resolution of our models in order to improve the quality of multi-day weather forecasts. And the main reason of this is because we are about to hit a hard ceiling when it comes to power consumption. We just cannot pay for the energy anymore that our machines are going to consume. And particularly in the developing world, it's not clear how this is going to scale. Unfortunately, all the other methods that we know of do not deliver the accuracy that we need when it comes to multi-day forecasts. So what are we going to do? Fortunately, the past years have seen incredible advances in neural network modeling. By learning physics from data, deep learning promises to achieve weather forecasting at far lower compute requirements. Harvesting the power of deep neural networks thus promises to lift the power ceiling that we are facing, and also to lower the bar for entry for countries such as Uganda, so they can run their own specialized forecasting services. So this is precisely at the heart of our project. We are using machine learning to learn data-driven weather forecasting models with lightning-fast inference. My colleague Daniela is going to tell you now how exactly we are going to do that.
Thank you very much, Christian. So first thing first, let's define the problem. We want to show how machine learning can help predicting precipitation up to a few days with global view to the Earth, including in the algorithm some kind of physical understanding of the atmospheric system. We can now focus on the single tokens in this statement. First, we decided for precipitation itself, since it is one of the most impactful atmospheric variables, especially in scenarios like roses. But how do we represent precipitation? Should we represent it in a numerical way, with, let's say, values of millimeters of rain falling in an hour, or with a more humor-friendly representation, like light rain, heavy rain, storms? And moreover, rain itself exposes some big challenges. It falls on a very small portion of the Earth at every single moment. And even there, light rain happens way more frequently than, let's say, a thunderstorm. And this leads to a very imbalanced learning problem. Next one is the future. How do we represent it? We can represent the future as a continuum series of predictions, let's say one every hour, or we can do a single shot prediction, asking the system to predict a specific date, like tomorrow at 5 p.m. And for how long should we aim to predict? A few hours is too short for most applications, just think about roses, and weeks in advance will bring in complexities way beyond the scope of the project. Few days, 3 to 5, is a good compromise for our study and for a usable application. Scale. So we aim for a global precipitation forecasts, but with local discretization, because at the end, there's no one interested in a precipitation averaged over the whole Europe. But you can see that the weather in the UK may be influenced by the weather above the US 3 days ago, right? So this fact brings in an overloading amount of data to be considered. And it is the order of terabytes of data for every single year. And we have many, many variables, from temperature to humidity to pressures. But at the end, maybe not all the variables are going to influence the precipitation, and maybe not even all of them are useful ones, since they can't be moved easily forward in time. This leaves us with the challenge of choosing the minimum set of variables that can allow us to achieve precipitation forecasting. And since we're dealing with the whole globe, we need to take care of the diverse landscapes, like land, sea, mountains will just behave differently, and we need to acknowledge that. And finally, someone could say, yeah, but we study weather since the last century, and we already have a lot of algorithms to predict precipitation. Isn't there a way to exploit them to help our system? We think this is a very good point indeed. Adding some level of physical understanding to the system will not only help our algorithm to learn a better representation, but it will also help the end user, since the system itself will be able to explain to some degree the Earth state it foresees, increasing the trust on the predictions. To do so, we decided to exploit the ERA5 dataset by ACMWF. This dataset contains hourly estimates of a large number of atmospheric, land, or oceanic climate variables from 1979 to 5 days ago. And as Christian described, Physics is not enough to describe the evolution of the atmosphere. For this reason, we want to include also some notion of stochasticity in an algorithm, leading to the issue of choosing the right representation for it, either using statistical equations directly in the system or sampling different futures from the same present. This has a huge impact on the structure of the proposed solution. I will now let Catherine describe our proposed methodology towards the digital twin of the Earth.
So now I will introduce to you our proposed model of digital twin Earth for the task of precipitation forecasting. This system that we have designed will have three main components. Firstly, we'll consider satellite imagery that are coming from satellites, as well as atmospheric states coming from numerical models, in addition to precipitation maps over the globe. So how do these three main data components come together for precipitation forecasting? I will now walk through 3 steps that we used in our framework. Firstly, we start from satellite imagery to go to prediction and estimation of the atmospheric state in a data assimilation step. Next, we focus on the atmospheric state space, and we want to be able to forecast what the future state would look like. As a third step, we focus on the future atmospheric state, and we want to be able to reconstruct what the global precipitation map looks like in a post-processing step. So together, these 3 steps come together, and when performed in sequence, form the crust of our digital twin Earth model. So here we can go from satellite observations through atmospheric states to a future precipitation state. And importantly, we believe that the introduction of the consideration of atmospheric states helps adding in physical constraints to our model, which enables medium range forecasting for precipitation. This is a key differentiator of our method against traditional data-driven methods. And we believe that by doing so, we will be able to forecast in the medium range into the future for about 72 hours, or in other words, 3 days. In this FDL project, we have decided to make use of this framework structure to break down our experiments into 3 parts, each corresponding to each stage of this framework. In this case, we want to be able to show feasibility and demonstrate each stage independently. And I will now go on to describe how we precisely do that in detail. Firstly, this is a step that corresponds to the data assimilation step, and we'll consider a set of experiments that will focus on taking a sequence of satellite observations, as well as other observations which might be simulated from Earth that are available on the satellite. This is for the purpose of reconstruction of an atmospheric state at time equals 0, which is the present. As our machine learning backend, we consider the use of convolutional recurrent neural network for this task. In addition, we would like to stress that we are not just predicting a limited set of atmospheric variables such as temperature, but we are actually corresponding our intuition as well as different empirical results that suggested that we can predict a wide range of atmospheric state variables. This includes other variables such as cloud, liquid, ice content, humidity, amongst others. In our second step of experiments, we are focusing on the atmospheric state space. Here, we're looking at the problem of state forecasting. Precisely, we are taking in consideration a history of atmospheric states going up to 12 hours in the past relative to the present. And we want to be able to predict and forecast the state at a lead time of up to 72 hours in the future. As Danielle has mentioned, we want to be able to include stochasticity in our framework. And therefore, we have borrowed techniques from video prediction to include, to adopt a method called stochastic generative adversarial network for this step. So this completes our forward modeling step and the set of experiments. Our third set of experiments focuses on the same time step reconstruction of precipitation from atmospheric state. Here, we are considering the use of pixel-wise fully connected networks for this task. And this ties in nicely to the last step in our framework, which is the post-processing step at a future time of t equals 72 hours. Now, this is a recap of how each of these set of experiments fit in together to form the whole picture of our digital twin Earth system. And I will now pass on to Valentina to explain how we are able to achieve feasibility in each of these.
Thank you, Catherine. Let's look at the preliminary results we had for each of these stages. Let's start from the state estimation, which given a set of observation of the Earth, which allows us to estimate the current state of the atmosphere. As Catherine said, for this step, we used a convolution on recurrent neural network so that we could feed into the model a sequence of observations, like the one that you see in the left-hand side of the slide, to output the single current state of the atmosphere. You see, still in the left-hand side of the slide, a comparison of the sequence of ground truth and the predictions of our model for two of the variables of the atmospheric state, the temperature one and the humidity ones. You can see overall that the model is able to capture the structure of these variables and also capture the specificities. For this task, no state-of-the-art data results are available, publicly available. This is why we compared instead different settings where we were feeding into the model different type of Earth observational data, but also and also a third set where we were feeding in also the last available state of the atmosphere, which will be outdated in a few days. Moving forward to the second stage of our system, which is the forecasting of the atmospheric state you can see here an example of the predictions that are made by our model. Here we needed to consider the chaotic nature of the Earth system. This is why we implemented a stochastic model for this purpose. And you can see, for instance, two different outcomes for our model over the area of Australia. Even though these don't differ that much, probably because for the time window 3 days, the possible state of the Earth don't differ that much between each other. We compared also our results with respect to reconstruction error that we get over time. For instance, if we look at the results we get for the temperature variable, you can see that our results compare very well with some baselines. For instance, they compare very well also with coarse operational forecasting systems, like the integrated forecasting system that you see reported here. But also we can see the value of using a stochastic system for this task, because when compared to the deterministic model recently proposed in the weather bench paper, you can see that we are able to improve over those results. Finally, our last step, which consisted in estimating the precipitation intensity given the state of the atmosphere. We tackled this task as a segmentation task by defining 4 different classes depending on the intensity of the precipitation accumulated over 3 hours, going from no precipitation to heavy rains. You can see here in small the ground truth for March 2019 and the predictions below that we had with our model. Overall, we can say that our model is able to capture the dynamics of this system, even though we don't feed into the model any temporal information. You can see also that our model is pretty accurate in distinguishing between rain and no rain. However, you can notice that it's a bit too confident in the heavy rain. It oversamples a bit. If we look at the F1 scores for each of these classes and compare it to the results of the ERA5 reanalysis dataset, you can see that our model can reproduce these results pretty well, apart from the drizzle class, which seems to be trickier to model. So the results that I just illustrated are for each of these steps individually. This is because the goal of our project was really to prove the feasibility of these tasks. Now that we achieved that for all the 3 stages, we can put everything together in an end-to-end system to really forecast the precipitation intensity given observation of the Earth. And now I pass it back to Christian to conclude the presentation.
Thanks, Valentina. So why do our results matter? Well, clearly, we have taken some exciting first steps in order to demonstrate that deep learning can help overcome the power ceiling that numerical weather forecasting is predicted to hit very soon. And here's a summary of our contributions. So before the past 2 months, there were no publicly available results on estimating some important state variables from simulated satellite data. Now we've got that. Secondly, we improved some of the publicly available benchmarks to do with state forecasting over a 3-day period, including results on temperature, and we added some new results on some of the so-called wet variables that are particularly strongly correlated with precipitation. And lastly, we also include a novel method of estimating precipitation from Earth observation data using neural networks. However, our contributions don't stop there. We are also going to open source a framework called PyRain, which we hope will enable future researchers in this domain to accelerate progress towards our vision of creating a true digital twin of our Earth. And remember, our overarching ambition is to provide 5-day forecasts, weather forecasts for the whole planet as soon as possible, so we can help farmers such as Rosie in Uganda. Okay, so I would like to conclude by acknowledging all the amazing people who have helped us with this project. These include, for example, Stefan Rasp, and a whole host of other experts. Thank you so much for helping us during the duration of our project. And in addition, of course, I would like to thank our amazing partners and sponsors, and in particular, the University of Oxford and the Frontier Development Lab, but also NVIDIA and SCAN, who have been providing us with some amazing DGX service, and the Google Cloud team, who has given us access to their resources. Thank you very much, everybody. Without your support, this project wouldn't have been possible. Have a good night.
Thank you so much, team. It was really exciting. I was getting text messages from my my climate scientist friends who are like raving about it as you were presenting, and really, I was so thrilled to see your results. So thank you so much. So again, I'd like to pass it over to our panel. You know, what caught your eye? What ideas were sparked? You know, what should the audience take away from this? And I think we're going to kick off with Massey.
Yeah, well, I'm kind of really thrilled about this work. And, you know, in a sense, actually, I think you guys have been really, really humble in presenting it. But this actually is massive progress. I mean, I think actually kind of really moving the bar in terms of using AI to not only kind of make better these simulations, but also make them, as you pointed out, cheaper so that they can be run at scale. I think actually is really kind of a path in the future. As you probably know, like there is a lot of momentum in this area from a lot of companies, including Google. And one of the things actually that really inspires me is this idea that we want to use technology in a sense to solve these big climate problems and these big kind of global problems. But at the same time, actually, we don't want to make that technology actually becomes a problem in its own by actually kind of consuming actually an immense amount of resources. And also there is another point that I want to kind of point out in this work that I think is really, really important. Right now, actually, this kind of technologies and capabilities where they exist are not really kind of accessible to a lot of like underdeveloped countries and people. And this kind of work actually can help democratize that. One point on the technical side of things that I think is really exciting is this idea of like having machine learning physics. I think actually that's really exciting. I have a physics background, and so on one side actually kind of I like actually my equations, but the idea of having machines being able to sift through this data and understand the behavior of natural world in a way that probably kind of we humans actually kind of cannot cope with, I think is super exciting. One last word that actually would kind of mention here, I wouldn't kind of feel too bad about some of the kind of predictions not being on par with the state-of-the-art models. Those state-of-the-art models, just kind of to remind the audience, are usually kind of come back actually from like 60 or 100 years of research and iteration. We're really just starting with this, and you guys already kind of are almost on par on most of the metrics. So I think actually you guys should just give yourself a pat on the back and kind of, I really kind of hope actually that this actually kind of continues and scales as you actually mentioned. Congratulations.
Thanks, Massey. Alison.
I love that you've focused on Rosie in Africa, and I'm actually doing a talk at a very big event based in South Africa, and I'm definitely going to be mentioning this. I happen to work with Maasai, and as symbiotic with nature as they are, you know, they all have mobile phones, and when it gets to the stage that you can put this into an app, it will be absolutely profound, because for them, they generally don't have any water. And to know when to prepare for a massive downpour that you tend to get in, say, places like Amboseli in Kenya is just incredible. Back home, or actually in Germany, we've been working with some very big car manufacturers to do a digital twin of just their production facilities, so we can use lots of simulations and AI practicing in simulation prior to putting this into operation. And the fact that you can do this now on a global scale is just incredible. And then to be able to send that data, you know, via, say, a mobile app is incredible. And we're also, we've been doing for quite a few years now a lot of work with harmonic dwarfs, with ECMWF and the Escape project. So I look forward to you know, working with you in the future to actually accelerate the mathematics with the GPUs going forward. Future work, and this would go for the clouds as well. You know, if you're using LSTM, take a look at Sepp Hochreiter's upgrade to LSTM. He's basically put attention into the pipeline, and it'd be interesting to see some results, because when you're predicting 72 hours ahead, attention is really going to make a significant difference. So have a look at his latest hot field layers. But otherwise, fantastic.
Thanks, Alison. Julian, you've got the mic.
I'll try to be shorter this time, but I want to pile on what Massimo, just said. Try to imagine how these models currently that, do your weather forecast are developed. They are a massive bunch of equations that come from fluid dynamics, from wave motion, that are massive systems of partial differential equations that have been developed and honed over, more than a century. You have entire labs, numerical analysis lab, who are focused entirely on trying to solve this huge set of equations. And so far, the best way has been to slice the Earth in little cubes and try to do some numerical propagation from one cube to the other. And that is 100 years of refinement, massive amounts of computation to be able to try to lower, to make these little cubes smaller and the approximation better. And now what you team have done, coming in and say, well, you know what, we're just going to ignore all the physics knowledge that's baked into these models, and we're going to throw stochastics again at it. It really reminds me of my reaction on my first day when I joined DeepMind back in 2012. And I woke on my first day, and I've got Demis presenting, okay, yeah, we want to do, you know, Atari action prediction. Like, hold on, you're trying to make a regression on a 30,000 dimensional space? That even possible? And there's very much the same feeling here. Like, you're gonna simulate the whole Earth and all the complex dynamics with again, without giving any physics way there. And so when you put this chart at the end where you're just the story behind these two bars, which are just exactly on the same level with the UR5 model, physical model, and just next to it, your SGAN model with no knowledge of physics, with 2 months development, and they're the exact same level of precision. It's almost disgusting for all the people who've worked on this numerical model for years. I think that's really exciting because you are just at the very beginning, and I'm really looking forward to where you're going to push it.
Awesome. Thanks so much to our panel. Okay, so we're going to change gears slightly. Of course, the other infrastructure that we'll need to build a digital twin is a new era of Earth observation technology. And this, of course, means launching massive constellations into low Earth orbit. But of course, this is a problem for our friends in mission operations. And so we're going to talk about that now in a moment. So stay tuned and we'll see you for the constellations team.